You're muted, Mihir.
Oh, no. See, that's why I did that.
Yeah, yeah.
Okay, so I just want to make sure that you can hear me now. All right, perfect. So, yeah, so let's just start it with ImageBind. It's one of the most interesting papers that I've read in a while. And one of the main concepts behind it is like, that's how the authors describe it. It's like when you go out to the beach and you see a dog and you hear a dog with the waves of the beach, then you immediately have a picture in the mind with the dog and the waves, right? So what essentially that your mind does, it relates the sounds of the dog barking and the waves, and it generates an image in your head, and that's essentially what you see. So your brain has this understanding of the world where each and every part of the subject, like the sound and the image of the dog, are inherently connected. And this is something as we move towards, building foundational models for robotics or basically any other field. This inherent property is required base, so that there are different modalities which are intertwined with each other. And this paper is like the first step towards it. So previously speaking, how zero shot classification models work, like for example, we take clip, it it is trained on huge amounts of image and text data, and then it can only predict it can only predict, the given an image, it can only predict the text of it, or given the text, it can only predict the image of it. So if you give it an image of a dog, it can't actually tell you if it can actually tell you about the audio or the barking of the dog. It can only tell you about the text. So this is something that these models are facing. They're only able to predict the modalities they have been trained on. And if we wanted to train such a model where all six modalities are intertwined with each other, there was a general consensus that there must be such data set where all six modalities should coexist, which is obviously very, very difficult to make, very difficult. So one of the key points of this paper that I'll be explaining in this presentation would be a joint embedding space, how the teams come up with it and how it is trained. The whole multi-model learning, which allows you. This paper describes six modalities. So how training between just using three modalities, image and two other pairs, can lead to the alignment of the the pairs which have not been trained together. So this results in the emergent zero-shot classification. Even though the modalities are not directly trained, they are able to predict. Uh, One modality can be used to predict the another modality, even though they have not been trained together. And finally, I'll be describing how this paper plans to implement it. So just to give you a high-level overview of what the paper describes. So given six different modalities, image, text, audio, depth, and thermal, and IMU, uh, these all six modalities are paired with each other without using the data sets which have all the six modalities. This extends the zero shot capabilities in the sense that it leads to the uh, emergent zero shot capabilities. For example, if an image is paired, for example, image and another modality are trained together, and the same image where the second modality is trained together, then modality one and two are essentially aligned. And this is what the teams observe while training it. So let's talk about how they achieve this joint embedding. So what this paper uses image as the backbone of training. So for example, image and a naturally occurring data. For example, there is a huge data set of image and text, and essentially this model also has provisions to use large-scale vision models such as CLIP. So we can use the already pre-trained encoders along with naturally occurring data, which is like video and audio, which is very widely prevalent, and image and depth. There are a lot of data sets, especially used for self-driving training for image and depth. And these kind of data sets are very prevalent. So we don't need all six modalities. They just use whatever we have and whatever we have on scale. So this is what the paper described. For example, we have aligned the embeddings of image and text and depth and sensor and the web videos. So these are very prevalent and easy to get data sets. And as you can see, even though that we have trained these data, we have explicitly trained, aligned the embeddings of of image and text and depth and image, we can see that the alignments of image and audio they have been aligned, and these emergent alignments are so strong that this paper actually has the highest text to audio. It has achieved the state of the art for text to audio, just with the emergent aligning. So there was no use of audio to text data set, any other data sets. It just relied on the emergent aligning to get that state of the art. So, mathematically speaking, what this described is given a pair of modalities, I and M, it is then passed on, the embeddings are produced using deep networks. I'll be explaining how they produce the embeddings. Uh, so let's say Q of I, which I represents the number of data. So if there are I images, then Qi represents the embeddings of I images, and K of I represents the uh, embeddings of other modalities. Now this could be anything, could be text, could be thermal, could be IMU, could be anything. What main thing that this requires is there should be images to go through it. And then these embeddings are then normalized, and then they're optimized using the InfoNCE loss. So before I dive into what InfoNCE loss is, I thought I would give a short overview of what contrastive learning is, because this is essentially a case of contrastive learning. Um, yeah. So contrastive learning basically is self-supervised learning, which aims to learn the low-dimensional representation of data. So the whole point here is to enable zero-shot classification. So which means that we're not only predicting the classes which have been presented to us, but more like the classes which have not been seen through training, that can also be predicted. So given a representation of, just to explain it in very high level terms, if, for example, if we have like images of dogs and cats and we have it in a representation space, what we want to make sure is that the similar data, so like different images of dogs, they're aligned, meaning that the distance between x1 and x2, which are basically the embeddings of images of dogs, they are minimized, whereas the embeddings between the dissimilar data, which might be the images of dogs and cats, they should be maximized. So this type of learning is usually done through self-supervised representation, which basically means that there is no need of labels. So it is not given to us that these images are of dogs. Uh, but using the contrastive loss, we make sure that the similar data points are minimized, whereas which are not similar, they are maximized. Uh, I won't be going into depth about the InfoNCE laws and how it is derived because it is a hugely vast topic. But just to give you a brief overview and how it is used in this paper. So informative noise contrastive estimation loss, also known as info loss, is used in various self-supervised and unsupervised learning methods. And as I said before, it assigns a higher similar score to the pairs of data which are similar to each other, and a lower score which are negative. And then it uses a softmax to turn these into probabilities, and it is then put into the negative log likelihood for the final loss. So as you can see, this is the exact same, using the exact same terminologies that are used for image encoding, which was like Q of I and other modalities. This is the same formula which has been in the paper. So just to explain how this makes sense, um, the numerator, the exponent of Q of I times K of I, this will tell us how similar the data is. So how the embeddings of image and other modalities are similar to each other, divided by tau. So tau is the scale, uh, is is the temperature. So basically, if the temperature is lower, then it means that it'll, it'll sharpen the probability curve. Uh, Whereas if it is very low, then it will flatten the curve. So this paper uses actually tau of 0.07, and it has experimented a lot, which I'm gonna just demonstrate it at the end, just from the paper. And this whole expression is then put into an exponential, which basically means it can't be negative, divided by the same expression and the similarity of the images with the modalities which are not similar to the images. So, like the images with images, and for example, text which are not similar to each other. And then it is then put into a negative log likelihood. So basically, if the given modalities are not similar to each other, negative log will tend to increase the loss, and it'll decrease for if they're actually similar. So I hope this makes sense. Uh, if it does not, then there is a good video on NCE loss. I guess people should uh, get read the paper, go through that video, and InfoNCE's loss is basically using cross entropy. So hopefully this kind of makes sense just to understand what ImageBind is about.
So is this the same loss as clip loss?
I yeah, I think they use the InfoNCE loss as well. Yeah, I think so. I don't actually remember what the exact loss function they use for clip.
Mm-hmm. So basically, they're,
Mhm.
I guess, using the same sort of approach as clip, but
Yeah,
expanding it.
yeah. Clip is a form of clip uses contrastive learning, so it's exactly the same approach, but uh, what the teams have found out is there is a case of emergent alignment, which means aligning different modalities tend to align modalities with themselves even without explicit training. So this is what the paper talked about. So like if we have trained. Oh, by the way, another thing I did not mention. Yeah. So a loss function of I comma m and m comma I are summed, and then it is used for training. So images are mapped to modalities and modalities are mapped to images. So yeah. Anyhow, so what the teams noticed, and this is a fundamental part of the ImageBind paper, is the emergent alignment, which basically means if we are using image to align with one modality, for example, text, and we're using an image to align with another modality, which let's just say audio, the teams notice that there's a strong alignment between the two modalities because this is a joint embedding phase. Uh, they've they've actually seen that the audio and the text are aligned with each other's as well. And this means there's no need of explicit training. Uh, and in this case, they achieve the state of the art for text to audio classification without using any audio to text uh, data set. And this is really the main point of ImageBind paper. This is the really start of where we can see that we don't really need to have specialized data sets to achieve similar kind of tasks. And it is just a starting. So really delving deeper into how these were implemented. So they use transformers for all architecture. Hopefully everyone knows what transformer is. If they don't, there is a good blog by Jay Alamo. Really intuitive, gives an understanding of attention and how transformers work. Basically, just to put it in layman terms, it's similar. It's like CNNs but better. So it has better encoding properties. Just to give a high level explanation. So I guess it's a higher level explanation. Anyways, I'll give you guys a link to understand how transformers work. Uh, yeah, so for images they use straight up vision transformers, and for video they use two frame video clips sampled from 2 seconds, and then it is passed to the same visual transformers as the image. For audio, it is generalized. Pretty much everyone uses MEL spectrograms uh, at 1600 kilohertz. So that's what they do as well. So when you have a MEL spectrogram, it essentially is a 2D signal, and which is basically an image. So you can just put that into VIT. The authors use a patch size of 16 and stride of 10. This is what they use to achieve the state of the art. Um, and the depth maps, they are converted into disparity maps for scale invariance, which basically means if the data sets have, there is different variations of data set. So it shouldn't matter what the scale of what the inherent properties of cameras are. So it is scale invariant. And for IMU signals, 5-second clips are projected onto 1D convolution, which is then encoded into transformer. I'm just giving you a basic overview of how these modalities are encoded. For more details, you can just go and read the paper. And yeah, so there was so these separate embeddings are created for different modalities. And for each encodings, it is then followed by a fixed sized, just a linear projection, just a linear ray to convert it into a fixed sized dimensional embedding, so that every embedding's dimension is the same. They're then normalized and just fed into the InfoNCE loss. And also, I think I've mentioned this before, that ImageBind has, it can use pre-trained models. So you don't have to have image and text data set. You can just use, for image and text, we can just use clip or open clip, which has been previously trained. So this is basically it. Um, just for final points, I'm just gonna go and explain it from the paper itself. Give me a sec. Uh, okay, can you see the paper?
Yeah.
Oh, perfect. Uh, okay, so yeah, so one thing I would just wanted to show is the results that they have obtained. So these are the images, these are the embedding, the emergent zero class classification results for ImageBind. And the one which are highlighted in blue, basically this part, they are emergent, which means that there was no explicit data sets used to train them. So as you can see from the results, they're not super high. Like if we compare it to the absolute state of the art, but it gives a promising start to such emergent zero-class classification. And to be fair, when this paper was published, not a there's no actual emergent zero-class results. This is like the first thing that has generated into it, which has given this term. So as you can see from the results, it's nowhere near the absolute state of the art. But given that we don't need, a very highly curated data set to have these modalities aligned with each other or somewhat aligned with each other, these results are pretty promising.
So
Um,
I just want to ask a question about that table.
yeah.
Um, is it correct that there's no state-of-the-art benchmark for, what is it, thermal and inertia? There's like no models that have tried to predict on those data sets or what?
Thermal and inertia.
Like the
I
last two
mean,
columns, there's no comparison.
yeah, there's no state of the art for some reason. I have no clue.
Like nobody uses
Yeah.
thermal and inertia data sets.
I, like, how would you even align thermal and IMUs? I've absolutely no clue about it, to be fair.
Hmm.
Yeah,
And then
that is
also,
interesting.
I guess, so you said that they get state-of-the-art for text to audio,
For audio to text, yeah.
or audio to text, and which one is that in that table?
Mm,
Or is that a different table?
I mean, they've mentioned it here that they have achieved it.
Oh no, the state-of-the-art is for something else. That's for like a generative model, right?
Wait, I swear to God I read it, but you know what? I'll let you know where I read it, but I did though. This is one of the main points about this paper that, wait, it was, I think, in the introduction. Recently, a major um, ImageBind outperforms animation. Um, they did mention it. I wouldn't have said it, to be fair. You know
Is it
what? I'll let
table
y'all know.
3? Maybe it's the table 3 one. It says ImageBind outperforms prior methods on zero-shot retrieval. Maybe that's the one.
No, they explicitly mention it that we have achieved state of the art. Mm, mm. Oh,
Well,
man.
figure 1 says um, audio to text, audio to image generation using a pre-trained DALL-E 2. Are they like separating generation from classification? So it's
That is generation. That's not yeah. So that's also one of the things that I wanted to mention that especially where is it? Mm, in the applications of apart from the general multimodal and embedding space arithmetic, like what they experimented was that these diffusion models use text to generate images, since they can align those texts to audios as well. They they created a model which can use just an audio to generate an image. So you can basically add of the barking noises, and it'll hopefully generate the image of a dog. So yeah, so this is also one of the things that these authors have achieved. So upgrading text-based detectors to audio-based. You know what? I will find it because I'm pretty sure they mentioned it. I'm just not able to find it right now. So yeah. Mm, So this is what basically the gist of paper is, that although the alignment of these modalities are not strong as compared to, let's say, if we have direct data sets of image or some other modalities, but the fact that just training with three modalities help us achieve alignment between the modalities which were not even trained, uh, is a notable achievement, or a start of uh, a series of paper which can even discuss the emergent zero shot classification, because this term wasn't even existing before this paper, and they didn't have anything to compare it with. So uh, what I want to say just in the end, that this paper can, more research from this paper can help develop foundation models, which will hopefully, take in multi inputs of different modalities, and help perform a particular task. So this is a stepping stone in realizing, and just in because right now we don't have the data set which can have data for each and every modality, but maybe we don't really require such a data set. So this is just a stepping stone for joint embeddings, to achieving joint embeddings over a large number of modalities. Yeah.
I had a question. So it seems here that they train like the model from scratch, basically. I wonder if you already
Mm.
had like an existing text to image model, or pick any two modalities and assume that you already have an existing model for that. How could you like fine tune it so that it agrees with the other modalities?
Yeah, so actually for image, so what they used was image to text and then image to audio, to get audio to text, the alignment. So you don't have to train it from scratch. You can use, so the authors here used OpenClip or Clip, and Clip to, if this section really describes what kind of data sets they use. So you don't really have data sets, and you can even use the already pre-trained encoders. So it is not really necessary to train it from scratch. Uh, but given that there are not, open source encoders apart from Clip and OpenClip I don't think we have really image to audio pre-trained encoders. But for the ones they have used OpenClip, so there is no requirement of retraining it from scratch.
Oh, cool. Yeah, I misunderstood that part. So they're just adding a neural
Yeah.
network on top of the embeddings.
Neural net, just a linear projection is added to make sure the dimensions of each embeddings are the same. That's it.
So it's just a linear. Wow, interesting.
So the encoder, and depending on which encodings you have, it might be of different sizes. So just one linear layer to get it to the same size, same size, which is represented as D. So just to get it on the same size, and that's it. And then it's normalized fed into InfoNCE. Yeah.
Yeah, I'd be curious if you made a more complicated network there, how performance would change.
Yeah.
Are they fine? So they're not fine tuning the base model. It's just a linear projection. Did I get that right?
Yeah. They're not fine tuning. This is, yeah, I think it is described here. Yeah, we use separate encoders for text image, and just a specific linear projection head on each encoder to obtain a fixed D-size dimensional embeddings. It is normalized and used in InfoNCE loss.
I guess they could if they wanted to fine tune the model itself, right?
Fine
What,
tune as in?
like, for instance, if you start with the baseline clip model, now you have all this new data that you can use to potentially make that clip model even better, right? So, like, you know what I'm saying? You could, now that you have this approach of aligning the, let's say, clip image space with all the other modalities, then you can make
Okay.
the clip image space itself better, right?
Yeah, but the thing is, these modalities which are aligning without training, they're not as aligned as having, directly aligned embeddings of, let's say, image to text. So the performance of ImageBind is still not at par with the models which are directly utilizing the data sets which have direct pairs of image or a modality.
Right, but let's say
Apart from
that
the
let's say you take that model that's been trained on the full paired data set, you use that as a starting point, and now you can add some more modalities. Doesn't that improve all the modalities?
It does, yeah. I think it should.
Doesn't that mean that they should, in theory, be able to get state of the art over all of the modalities, assuming that they use the same baseline as this current state of the art?
Hmm.
You know what I mean? If you start with state of the art that was only trained with text image, then you use that as a starting point to add more data sets that are not just text image, then I would assume that you should, in theory, you would always do at least as good as the state of the art because you're starting with state of the art. Shouldn't you get even better than state of the art given now there's more data?
Yes, that kind of makes sense. Although, um, hmm, that's a good point though. Okay, uh, okay. So the thing is, so when we have, so for example, image and the modality one, and then we train image and modality two. But when you're training another modality, when training image with another modality, the image and the modality one's encodings are locked. So they are not changed while you're training the other one. So I don't think it'll affect the performance of some other model. Or at least that's what authors said, like the other models are locked. They're not affected unless and until you're making inferences from it. So maybe that has to do with it, but
Yeah, that makes sense. I'm just thinking
mm,
like, you know, there's the potential there. It feels like there's the potential there if they didn't completely lock it, because more data versus this, the same amount of data, you add more data to it, and you have these more modalities. I would think everything can improve, unless
but
it
then
somehow
again, then there
noises it.
is, yeah, then again, if right now we have amazing, performance, with Clip, we have amazing image to text alignment, and let's just say that we have another model of audio to of image to audio, but it is not as good. The alignment of these modalities are not as good as image to text. Wouldn't, this case, mess up the already, the state of the art image to text we already have? Because the other one is not that aligned with, these modalities are not aligned with each other. So if it can increase the performance, then it might even decrease it the if the if let's just say that we're using already pre-trained encoders. The encoders are not that aligned with each other. So then it can also mess up the state of the art. It can go, if
Yeah,
it can
I
improve it,
that
then it can.
that's a great point. I feel like that should definitely be something to that should be explored, because I could see it going both
Mm.
ways. Yeah, like it could make it more noisy, and so it gets
Yeah.
worse, or it could potentially get better. I'm
Yeah.
not convinced either way, and it doesn't look like they tested it.
Although this paper was released by, Facebook, Meta AI, um, first, even though this was on contrastive learning, for this exact reason that, we deal with a lot of noise and contrastive learning. Jan LeCun, for some reason, is not a big fan of contrastive learning. Like he explicitly says on Twitter that there are better ways to go about than self-supervised learning. And when I was reading about this paper, I came across the tweet from him, and then he was replying to the tweet saying that yeah, although we have published this paper, there are a lot of ways to go apart from self-supervised learning. Now, I don't really exactly know what exactly he's referring to, like what are the kind of techniques that can actually help us get the same, like the similar effects as ImageBind, but I'm just stating that he is not a big fan of self-supervised learning.
Yeah, I think he likes regularized models. He has like this whole talk on, yeah, on his opinions.
Yeah. Yeah.
What
I
is
think the
the,
oh, go ahead.
oh, sorry, I just want to ask, what is the dimensionality of the embedding space? Is it like bigger than Clip or is it comparable?
Um, I have, I, mm, what they, I don't know because as far as I've read, they haven't explicitly mentioned what dimensionality they're dealing with. They just mentioned D to make sure that the sizes are the same. And then they have at the seventh and the eighth page, they have wait, I think
I guess I was just thinking in terms of Paul's question, because if you have already like an embedding space and you're trying to map even more things into that embedding, like align more things, it seems to me maybe like you have less freedom.
Yeah, I would assume it. I mean, I guess like if they start out with a certain model and they're not trained from scratch, it would be whatever the same
yes.
one is.
Okay, it says we vary the projection head used for each encoder from linear layer with to an MLP with 768 hidden dimensions. The table in 5B shows that the linear projection outperforms better for both modalities. I guess they use the same 768. By what? I have no clue. Doesn't explicitly mention. I mean, I can figure it out from going through their code. It is actually available on GitHub. So their implementation of ImageBind. Mm. And what they use, and yeah, so the temperature they use is 0.07. They've published their studies using different amount of different temperatures and different training epochs. So in 5B, table 5B.
I think it's
Projection head.
768 dimensions. I'm
Yeah,
looking at their code.
that's what they mentioned in the paper as well, yeah. I don't think the size of the encoding really matters. I think the idea is just to have each embeddings of the same size, because image to text, they might have some size, then audio might have some other size. So just to get it in the same 768, in this case 768 size embeddings. Uh, the linear projection head is used, and they've also experimented with MLP, but linear projection works better. Works better than an NLP, or yeah. Mm, yeah. at the end it says it's a research tool that cannot be used for real world applications. I mean, given the performance of this model, we really need to have better better performance if we want to use ImageBind, although because right now using specialized models, they give us better. I mean, that's what I guess for whole machine learning AI thing, that if we use a specialized data set, it gives us a better performance. So yeah, it's just an introduction to using different data sets to get different predictions from the one that we have trained on. Something which was never done. This is the first paper that came out with, giving the term emergent zero-shot classification. So it's just starting. We'll have to see what other papers come up, So
So I'm curious about in the abstract I'm looking at, it says ImageBind enables novel emergent applications, like you were saying. The emergent capabilities improve the strength of the image encoder. So, like, what does that mean? It means that, like, it outperforms the base clip that it started from? Like,
we definitely can't outperform that. The emergent capabilities improve with the strength of image encoder.
improve with,
Basically
with the
means
strength.
if we have a better image to text or better image to another modality, the more aligned we have, the training the different modalities, the more the better is going to be the emergent zero-shot classification or zero-shot, alignment
Right.
between those
Yeah,
modalities.
I'm just reading too fast. And then the second part of it is setting a new state-of-the-art on emergent zero-shot recognition tasks across modalities, outperforming
Yeah,
specialist supervised models. So what,
yeah. Where is it?
that's the second half of that same sentence in the abstract. The emerging capabilities
Yeah, so
improve with the
that's
strength.
exactly what I was referring to. So they set a new state-of-the-art on emergency shot. Oh no. So a state-of-the-art on obviously they're gonna have a new state-of-the-art because there was no concept of emergent zero-shot capabilities. This is the first
Yeah,
paper that came out with it. Yeah, so like when they're discussing the results, they literally say that we don't really have something to compare it with, compare results with.
it's kind of
So they just
unfair
come.
to say that they've got state-of-the-art everything if they're the
Yeah,
first to
I
have
mean,
to
it's
measure.
not state of the art.
Uh,
Yeah, I mean, obviously, because it's like the first paper of
but
this
is that related to what
emergency.
you were saying before with the audio to text classification? Like it's the first
No,
emergent audio text. Is that?
maybe. Like I thought it might be too good to be true.
Because like when I read it, it does like so it says we set a new state of the art on emergent zero-shot recognition tasks, meaning that it doesn't set the new state of the art on non-emergent zero-shot recognition tasks, outperforming specialists. But how is it outperforming a specialist model if the specialist model is not emergent?
Okay, so if you come to like page third page, just in this emergent alignment of unseen pair of modalities. Like the last sentence states that we achieve state-of-the-art zero-shot text audio classification results without observing a single sampled pair of audio and text. They just mention it here without, you know, elaborating what that means. But I guess they're talking about,
Where's the stats on that? There's no table.
yeah. I mean, if we talk about the table, well, the table also does not make sense. The table that maybe we can put X is possible use. If you're looking at the table, then none of it actually surpasses the absolute state of the art.
Yeah, maybe someone can figure it out and post in the Discord if they find it.
State of the art class without observing a simple.
Yeah, so it's like that part I'm kind of confused about, and then there's also just the fact of like saying state of the art for emergent recognition tasks, even though they're the first to do emergent recognition tests. But then
Yeah.
they're saying it outperforms specialist supervised models on what? On the task that's never been done before, emergent. Like you can't say that you're outperforming the other model when the other model only did non-emergent recognition.
Yeah.
Because it's kind of weird because like you were saying before that, these are not outperforming the models that have the real actual paired data,
Oh yeah.
but that goes against the claim of the state-of-the-art zero-shot text audio classification results without observing a single sample of paired data.
Yeah.
So I was wondering,
I
like,
made that.
if
I
that's a
made that
true claim,
inference.
like,
Yeah, because I made that inference just looking at this table and just saying, yeah, the absolute state of the art is has a higher score than these ImageBind. So even these and it does not say that the emergent state, the emergent zero-shot classification has outperformed just the regular zero-shot classification, except audio to text, which is just this one single sentence. We achieve state-of-the-art zero-shot text audio classification
yeah,
without
but
observing
it's like it's an important point though, because if you can, at least in one domain even, show that your emergent properties allow you to outperform a model trained only on the paired data, that suggests, going back to the other question I had, like you can use emergent models to improve the standard model potentially.
Yeah.
Otherwise, like the current results, if we exclude this sentence that doesn't seem to have the data currently to back it up, then I guess the thing is like, what's the point of having emergent models, assuming that you do have the paired data? Like, is it only useful if you can't otherwise get access to a data set that has the paired data, or a large enough data set that has paired data?
Or for doing tasks which has multi-model inputs. For example, the website of this paper really showed that. What is it? So you know, uh, taking multiple inputs and giving a singular output of it, but maybe developing the foundation models in robotics, which have images uh, and the IMU data, and even if we're using LiDAR, then we have depth, and using these three different sources to make decisions on based on driving. Maybe it is used for that. Maybe we can use it for you, because given that let's just assume that they have achieved this text to audio state of the art, because in their applications, it mentions that it can upgrading text-based detectors to audio-based. We have pre-trained text-based detection model uh, without training. Yeah, so as shown in figure 5, we can prompt the detector with barking sound to localize a dog. So basically doing tasks which takes in multiple inputs from different sensors to do a singular task. I think that's where it can be used. And obviously, also for example, if a model takes in, like what they've done with diffusion models. So like instead of giving text inputs to have audio to generate an image, we can just by having an emergent alignment between the text and the audio, they can just pass an audio to produce the same image. Uh, this is assuming that we don't have a good data set of audio to image, or we might have a data set, but it may take a large amount of training data to actually train another diffusion model which will take an audio. So I guess having these aligned embeddings can help us to have an easier implementation uh, of more of there's these models which are designed to have some other input but can now take in different modalities just because they're aligned using ImageBind. So I guess that's where it really that's where it can be implemented. But then again, in this case of diffusion, the output then really depends on how good the alignment is between audio and text. And if it is not that aligned, then it is worthless to even consider using audio. It'll be easier for us to use text. So
Yeah, thanks for that explanation.
yeah, just some last words. To really understand this paper, people should know about contrastive learning and even transformers in general. So I'll just uh, I didn't find some good source for contrastive learning, just using a lot of websites to and papers to learn it. But for transformers, I have this amazing source that people can refer to if they want to learn more. But I feel like we're just only 5 people, and I feel like we all know about transformers. So I don't
I
think
think
that's really necessary, right?
if you already have some resources though, like I'm sure people would benefit from it if you share it in the Discord.
Yeah.
The deep unsupervised learning course at UC Berkeley is really good for contrastive learning. I can post it in the chat.
Yeah, I have a look at it because I really want to understand in depth about it. And the way I described InfoNCE loss is currently the only way even I understand it, mathematically speaking. Uh, because I was not able to get in depth in the pure mathematics. So I really want to get into that. So I'll have a look.
I guess I can say something about like why are we talking about ImageBind in our more neuroimaging AI group is, we already use CLIP, right, to project a new third modality fMRI into CLIP image space, right? But I think this paper really, like you explained, it opens the door to have many modalities that all get linked to a single, in this case, image space. So imagine we have fMRI, we have EEG, MEG, FNIRS, all these neuroimaging modalities. We already know fMRI can be projected into CLIP image. We can potentially do the same thing, I think, with all the different neuroimaging modalities. So instead of thermal, inertia, audio, we have EEG, MEG, FNIRS. This is an important possibility because, you know, fMRI is so like it's so hard to get data for fMRI. It's like $1,000 an hour. You're inside of a large, heavy machine. You can't wear metal. You can't move around. But if you can create a really nice mapping between fMRI and clip image, and then a new mapping between maybe a portable neuroimaging technology to clip image, you could potentially really increase the utility of that modality, right?
Yeah, definitely. So in this case that they have used, text audio, for us, they could use fMRI, and some other neuroscience data types of data, and they are basically different types of modalities that we can use to, either help in foundation models. But since I've seen that these emergent modalities alignments are not really that good, so I was thinking, what if we use ImageBind in MindEye, but right now I feel like it might not be that useful. So yeah.
Right. Or it might be like just as good as using the base model, right? I'm not sure where the GitHub weights come from, but they probably used, I'm assuming, Clip or OpenClip, so it might just be identical in that
They've
case, I
used
guess.
OpenClip, yeah.
Mhm. So it might just be like identical kind of informativeness as the OpenClip weights, is what you're saying.
Yeah.
Yeah, I'd be interested if we can get a hold of like other modality image paired data sets and see if we can see if they're so that's one thing I'm really interested in. And then the other thing is like, can you like improve the base model using the other modalities? Because I'm still really curious about that because that would be an interesting avenue.
Another thing that I think of, it's like, okay, so we have image to text aligned. I guess you can only improve image to text alignment only if we have any other model which has a higher alignment of image to some other modality. Right. If we have if the alignment of image to text is better than image to some other modality, then it might improve the alignment of image to some other modality, but I don't think it can actually improve image to text. I don't know, just random thoughts at 2:30 a.m.
I
Yeah.
get that. At the same time, it's like, you know, I have the text caption of a cat, and it knows really well how to find the right text that goes to the cat and how to find the right picture that goes with the caption. But nowhere does it know like what the sound of a cat is like. Like this is
Yeah.
new information, right? And maybe this is a bad example of using a cat, but I could think of other auditory cues that do have a pictorial representation to it. You know what I mean? So like an image of a cat purring versus an image of a cat crying or something. Like you can't, I imagine there's some signal that you could extract from an emergent mapping to potentially improve the base mapping.
Yeah.
Okay, anyone else have questions or comments for me here? This was a great presentation. Thanks so much for guiding us through the paper.
Oh, no worries. I mean, I got to learn a lot, so it was more about me. Yeah.
Well, I really appreciate it. I'm sure the others do too. So thanks so much.
No worries. Thank you so much, guys, for letting me present. Yeah.
All right, so I guess we'll resume next week. See you guys.
Yeah.
Thanks for getting me here.
See you guys on Monday.